Welcome to the ET335 Module 4 Gate Truth Table lecture video. Here I'm showing transistor total pole circuits and TTL devices. TTL being transistor to transistor logic. And what we have here is our totem pole. Transistors, a resistor, and maybe a couple diodes. Here's the rest of the logic circuitry that control these two transistors, but this is our totem pole here. So if we want a high state, the top transistor is going to be on, bottom transistor is off, and we have a direct path to power. So this is a high, typically about 5 volts. If we want a low, the bottom transistor is going to be on, top transistor is off, which gives us a direct connection to ground, a low. Here we have one of the big no-nos of TTL devices. So we never tie the outputs of TTL devices together, because we could have one transistor on from power and the other transistor hooked to ground, and this is a direct short and will destroy the internal circuitry. So this is no good. Here we're looking at internal TTL totem pole circuits, and what we have are two current modes, sourcing and sinking. This is sourcing, where we're going to provide voltage to the load, a high. So the top transistor's on, bottom transistor's off, and we have a direct path from battery to our load. So conventional flow, we have a high. So anytime we have a high, it is considered a sourcing. Here we're showing the devices that provide a current source. So what we want to do is we want to make decoders, and decoders only should work on one input combination. So for its source mode, we should be using an AND, and we look here, we got 1, 1, 1, which is providing power, a high, or a NOR, 0, 0, 1, providing power. So if we want to use a decoder, we want to make sure that we're using one of these two devices. Here we're showing the other mode of sinking. We're going to provide a ground path. So I think of sinking to ground. So our top transistor would be off, bottom transistor on, so we have a direct path to ground, a low or a 0. Okay, so when our gate is low, we have a path to ground. So if we have a load on this, like a LED, it is going to light. So our LED should point to the device when we want sync mode, and we should provide a voltage. When we're doing sourcing mode, we should have opposite. We should have the LED pointing towards ground. Here we're showing the gates that we should be using when we're in sync mode, when we want to sync mode. So we have a NAND, 1, 1, 0. 0, we're providing a ground path for our LED, or an OR gate, 0, 0 equals 0, also providing a ground path. So these are the devices that we should be using if we want it in sync mode. Here we have the universal property of gates, where we could take one gate type and make other type logic devices. So if we take the inputs and tie them together on a NOR gate, it acts as an inverter. Okay, so if we take a NOR gate and tie an inverter on the inside, we have a OR gate. Okay, same thing happens with a NAND gate. So if we tie our inputs together, we're going to get an inverter. When we take a NAND gate and put an inverter on, we're going to get an AND gate. This does not work with ORs and ANDs, but it does work with the NORs and NANDs. Here we're showing the internal circuitry of a NAND TTL circuit. What we have here is 3 different areas. The first part, this is the logic here. This is a multi-emitter transistor input. Okay, so here we have our two inputs for our NAND gate. All right, that controls this interface circuit. This interface ties the two together. So we have our logic, interface, and our output totem pole. Okay, so in a sinking condition, this circuitry, being that these are both 5 volts, the transistor current will go in and turn this transistor on, which turns our lower transistor on, and we have a low output. Here we have our NAND TTL circuit set up for sourcing. So we have 0 volts on our NAND gate, 0 and 0, which are ground, which is going to turn our transistor off, which this pull-up resistor is going to turn our top transistor on, and we're going to provide a output, positive output, which is a logic 1. And you notice here 3.4 volts is not 5 volts like our TTL. That's because this circuit is taking up a lot of that voltage. So we're not going to get our 5 volt output. We're going to get a nominal 5 volts, which we'll look at the specs later, but it's going to be close to being high, but it will never be 5 volts. Here we have our open collector TTL devices. These are different than our standard TTL devices, that they have a open collector output. So this transistor allows us to sink more current. So we could sink up to 40 milliamps, which is better than our 20 milliamp. Our TTL high is only 40 microamps, but since we're providing our positive voltage and current from the outside, we could go much higher than that. So this circuit is used for driving higher current devices like a lamp or relay. And when you see an open collector gate, they're going to have this symbol on it. That shows the open collector device. Here we're showing our open collector devices again. So when the output is low, the transistor is in the sinking current and the LED or lamp will be on. So we'll have more current here, about twice as much current here. So when this device is low, we're going to provide a path. We are going to need an external pull-up resistor to make the LED work. Plus this device has no positive voltage, will not go high. We need to provide that externally. Here the internal resistance is built into our lamp. So when the output is high, the transistor is off and the current is 0, and the LED or lamp will be off. This device will only provide a high if connected to a pull-up resistor. So the good thing about this device is we could actually put different voltages on this than our TTL voltage. We could actually drive this lamp with 12 volts because all we're doing is providing a ground. Whenever we're designing with multisim, we should use only standard gates unless you intend to use an open collector gate. This is a common mistake students make, is by grabbing the wrong type of NAND gate. So if it is a open collector, it will not go high unless we put an external pull-up resistor, and the logic's not going to work. So we should always use standard gates: 7400 NAND, 7402 NOR, 7404 standard inverter, 748 AND gate, 7414 is an inverter with a Schmidt trigger, and 7432 OR gate. So we should always use the standard gates without having the issues. And another thing is, when replacing a gate, to be sure use the same family or the one of a faster speed, otherwise you'll have issues. Here's a device, Schottky clamp transistor. This would be the ones that are LS devices on our TTL circuits. And all way back, they've had a little battle between speed and propagation delay and power. So what they want to do is continually improve these devices where they're faster and use low power. Unfortunately, one usually degrades the other. But anyway, one of the devices, LS, utilizes a Schottky diode and a Schottky clamp transistor, and this prevents the device from going into saturation and allows it to switch quicker.